Is that Fabian? Yeah.
All right, thank you very much. Martin and I are going to talk about semantic dependencies in ontologies. And so the first part of the presentation, the first three sections, I will introduce two notions about semantic incongruity and semantic dependency. And these are more on the theoretical side. And then Martin will show in the last three sections how to use these theoretical notions and do actually something useful with them. And by useful, I mean evaluate real ontologies on a large scale. So I hope there's something for everybody here in the audience. Now, let me start by introducing the notion of semantic incongruity. And as you all probably are aware, ontologies have two different aspects. The first one is, well, ontologies consist of axioms, and these axioms provide us a formal semantics. And these are the things logicians are usually interested in. And if we have real ontologies like CABI, the chemical ontology, the axioms usually look like often very simple, often just subsumption axioms. Sometimes they are a little bit more complex, but you have something like class CABI 27732, subclass of CABI 27134. Now, sometimes people consider ontologies as logical theories, but just this simple example illustrates that that's only half of the information, because this is not really helpful unless you have the second part of the ontology, which are the annotations, which provide us the informal semantics. The annotations here in this particular case say, okay, the first class is caffeine, and then we get a definition what that is chemically. And of course, CABI has more information, but I'm just providing you a selection. And the second class is a class which I have difficulties to pronounce. I will try my best. Trimethylxanthine. Now, only with the help of the right side, the information in the annotations, we know now what the axiom is really supposed to represent. Namely that caffeine is a particular kind of trimethylxanthine. Now, on the left-hand side, that's the part that reasoners check. So if you have, for example, an inconsistency on in the logical axioms, your reasoner will help you to find it and tell you, oh, there's a bug. The right-hand side is something the reasoners won't look at, and because annotations are just ignored by the reasoners. But they are important, both are needed in order to get to the intended semantics, the intended models of the ontology. Just to illustrate, assuming I hack into CABI and sabotage it and replace on the right-hand side the label for caffeine by ethanol and the definition, adjust the definition accordingly, a primary alcohol, that is ethane, in which one of the hydrogens is substituted by a hydroxyl group. Now, the left-hand side is still unchanged, and since the formal semantics is unchanged, there is no logical inconsistency. The right-hand side on its own is fine too. I mean, the information about ethanol is correct. The information about trimethylxanthine hasn't changed. But if you take them together, there is clearly a bug, because now the class axioms on the left-hand side expresses that ethanol is a particular kind of trimethylxanthine, which is not correct. So what we have here is what we call semantic incongruity. The formal and the informal semantics are determined by the two different parts of the ontologies, one by the axioms, one by the often by speaking IRIs. That means IRIs which kind of looked like, or partially looked like, natural language terms, and then the annotations. And you have the two semantics, and both of them are complement to each other, and are supposed to provide you the intended interpretations. But if there's a clash between them, then this is a form of a bug, which we call semantic incongruity. Now, the main research question of this talk is, well, how do we check for it? As I mentioned earlier, our reasoners won't help you because they only look at the formal semantics. And this part of this question is going to be answered mainly by Martin in the second part of the presentation. I will look at something else, which has to do with the fact that the example I just gave you was very simplistic, because I just gave you, well, one axiom including a simple subsumption between two classes and said, well, here, that's some error. But, or rather, this assumption combined with the annotation leads you to an error. But in many cases, these semantic incongruities are the result of the interaction between many axioms and many terms that occur in the axioms. So, for example, here we have a small biological ontology, which talks about lungless salamanders. We know lungless salamanders are salamanders. Salamanders are amphibians. Amphibians are vertebrates. Vertebrates have as part respiratory organ, and respiratory organs are lungs, gills, and trachea, and nothing else. Now, each of these individually are plausible. I simplified the biology a bit, but just to make the point, each of them are relatively plausible. But then the logical consequences of it is that lungless salamanders have as a part a lung, gill, or trachea, and that's incorrect. I mean, it's maybe not obvious to anybody who knows are interested in these lungless salamanders, but they don't breathe with gills or trachea or lungs, but they breathe with their skin. Again, the ontology isn't inconsistent, but it's incongruous because the result, what it implies a statement which doesn't represent the intended semantics of the biologist who would develop such an ontology. So this example illustrates that semantic incongruity is not necessarily the result of only one axiom, but often the result of these dependencies that you have between the various terms in an ontology, which are the result of the logical axioms, in combination, of course, with their annotations. Now, I now introduce this new notion, semantic dependency, and as good ontologists, you will ask me, what do I mean with that semantic dependency? And the problem is I don't have a good answer for that, but I'll let me motivate it. So the idea that semantics of some terms in a language depend on the semantics of other terms is something very old. I mean, you will find that in semiotics starting with the early 20th century. But in the context of ontology development, we all probably aware of that. So, if you have, again, here toy ontology, and we assume we have this toy ontology involving the fish and mammal, if I add a new axiom here which says fish is disjoint with mammal, that doesn't just affect the semantics of fish and mammal, it also affects the semantics, for example, of cat, because we have the disjointness axiom is inherited from mammal to cat. Or if I make mammals now inanimate, of course, that's also inherited by cats in this ontology. So I hope that that it's clear to anybody who developed ontologies that the semantics of these terms aren't islands which are disconnected from everything else, but rather that if you change one part of your ontology, it may have unintended consequences for other parts of the ontology. So we have these semantic dependencies between terms, and they are important because they will play an important role for semantic incongruities, as we have seen. So now the question is, well, how do we know whether two terms are semantically dependent? And as I said, ideally, I would have a good definition, but and that's of course what we started to try to do and to give you. And you know, the first thing you do is collect intuitions. So, for example, again, the same toy ontology. Does the following hold if the semantics of A depends on the does the semantics of A depend on the semantics of B if A is a subclass of B? That's, I kind of assumed that in my previous examples, you know. So in this particular case, that would mean that cat depends on mammal. But does the opposite hold as well? Does mammal depend, does the semantics of mammal depend on cat? What about transitivity? If A depends on C and C depends on B, does A depend on C? Does A depend on B? It's not clear, I think. And if you agree to all of them, you get consequences which you might not like. For example, then in this particular case, cat would depend on vehicle. So, of course, you can look at other examples, that various examples. The problem is that different people have different notions of semantic dependency, and it's very, for this reasons, or different ideas and intuitions, and for this reason it's very hard to give a general notion or a general definition of semantic dependency. So instead of doing that, what we did is rather look at, instead of looking at the generic notion, we just looked at different kinds of dependencies, which are much easier to get hold on. And I will just illustrate that point with 3 examples. So one intuition is that two terms depend on each other, that if you break one, then the other breaks. What do I mean by break in the case of the an ontology? One way of making a mistake would be in providing an axiom which makes the class empty. So if a term has no instances, that's probably not intended in an ontology. And if this arrow propagates across the axioms in the ontology, then this constitutes a kind of dependency, which we call emptiness dependency. So the definition would be A, emptiness depends on B in an ontology, O, if any change that renders B empty entails the emptiness of A. Now this is semi-formal. We stated that, of course, in clear logic, but I think it's better to provide just the intuition here. So this is one notion, and then you get consequences. For example, in this particular case, if there are no mammals, there are no cats, so cats emptiness depends on mammal, but in this particular ontology, mammal wouldn't depend on cat, and mammal would not depend on fish. Or a different approach would be to go in the other direction and say, well, if a term denotes everything in an ontology, it's probably very useful. I mean, you might want one term in your ontology which denotes everything at the very top, but most of the terms probably shouldn't denote the universe of discourse. So this is captured by the everything depends relation. Everything depends on B in an ontology. If any change that renders A equivalent to everything, or the universal role in the case of roles, if that change entails the same for B, then A depends on B. Another example based on a different intuition has to do with growth. So if a new cat is born, a new mammal is born. So in that sense, there's a strong connection between the both terms. And this notion gives us a different form of dependency. A, growth depends on B. In an ontology, if adding new entities to the extension of A necessitates a growth of the extension of B. As I said, these are just 3 different examples. We have a few more, but they really lead to different notions of dependency and with different properties. So for example, if you're on axiom like A is a subclass of B and exists R C in your ontology, then according to emptiness dependency, A depends on B, C, and R, B, R, and C. According to everything dependency, A depends only on B, and nothing is entailed about dependency to R or C. And for growth dependency, we have the result that A depends on B and A depends on R. So the different definitions have really different properties. Here's another example where you have the axiom A is equivalent to B or for all R, C. If you have that in your ontology, according to emptiness dependency and growth dependency, B depends on A, and in the case of everything dependency, B depends on A and C depends on A. Sorry, I probably said that wrong. I meant B depends on A and C depends on A. So what's the preliminary summary? First of all, there's a notion of a semantic incongruity, which is the result of clash between formal and informal semantics, which we can't just automatically capture with automatic reasoning. And that is, in order to find out where to look for semantic incongruity, we need to consider the semantic dependency between the terms in our ontology. And this semantic dependency is a semantically justified relation between symbols, and the way we test these are by looking at properties which are inherited by the logical axioms in our ontology. So the logical properties were in our cases that a class is empty, or the class denotes the universe of discourse, or the class grows, and then we see what consequences does that have for other terms in the ontology. And that, by using these kinds of tests, we can check for semantic dependency, and then use groups of semantically dependent classes, and then look there whether they lead to semantic incongruity. And how that works was now explained by Martin in the second part of the talk, which is dependencies in practice.
Yeah, thanks. So let's look at dependencies in practice. So next slide. So yeah, here we have an example of an ontology. Obviously, we have a bunch of IRIs with subjunctional relations and some quantifiers. And by looking just at this ontology, we look at the axioms from the bottom, we can see that if OEO 2028 at the very right is empty, then OEO 139 on the bottom left is empty. And this emptiness then traverses up to OEO 54 on the top left. So we can see that obviously OEO 54 emptiness depends on OEO 2028. Is this helpful? That's debatable. And we don't know anything about these terms. And they are just numbers to us. We can't tell whether they are now good or bad, or whether this dependency is actually intended or unintended. We need, on the next slide, labels. And now this ontology actually makes more sense to us. We can now see that actually this dependency might not be intended, because we now see that it actually says that air emptiness depends on electricity export. And in other words, that means if there is no electricity export, there is no air, which is likely unintended. So there might be an error in this ontology, and yeah, actually one of the errors here would be the last axiom that should probably be replaced by the one on the bottom. So we can see that ontologies, these notions of dependency, can be helpful to detect errors in ontologies. But on the next slide, we now need to get those. And we need a mechanism first to derive semantic dependencies, and second, a way to evaluate them based on the annotations from our ontology. And next slide, we have already seen that these dependencies are have semantic definitions. Yeah, for example, for emptiness dependence, one could just use reasoning by, for example, introducing for every class, for a single class A, introduce a new axiom that says A is equivalent to bottom into the ontology, and then use a reasoner and derive all classes B that are now also equivalent to bottom, and then we know that B, emptiness, depends on A. Problem is, this is really computationally expensive. Actually, one of our this would be a whole reasoning task for every single class in our ontology. Unfortunately, one of our students was able to show that this is not just an artifact of the naivete of this idea, but this is actually a property of the emptiness dependence itself. A full, complete calculation of emptiness dependence is actually in 2nx time complete. So really expensive. We probably don't want to do that either. So on the next slide, we instead developed a syntactic calculus. So we looked at the individual axioms that one could write down in, for example, ALC or in EL, and developed a notion of, okay, if this axiom occurs, then these dependencies are derived. And we collect all these dependencies into a dependency graph. And because we want our dependency to be transitive, we compute the transitive closure. That yields a lot of dependencies. So we also remove some intuitively uninteresting ones. So for example, dependencies to subclasses. Those are usually not that interesting, and you can just check them by looking at your taxonomy. Yeah, or others are those that are just generalizations of other existing dependencies. Yeah, we remove those to keep stuff a bit more manageable. Okay, next slide. And well, we took this syntactic calculus and implemented it in a Rust library called Strix Roost, which is based on the Python OWL ontology processor. And all it does is, well, you give it an ontology, it parses said ontology, and it produces dependency for you based on different notions of dependency. You can also, if you want, get justifications for those dependencies, which are, well, the axioms that led for a given dependency. It also then produces a trail of axiom that led to this dependency. And as are all our tools, this is open source, developed in an open source fashion on GitHub. The QR code leads there, and you can look at it and use it freely. Okay, but now we have a tool, and on the next slide, obviously, we want to see what this tool actually does, whether this tool does something useful. And this whole approach does something useful. So we looked at two different ontologies. The first one was the open energy ontology, which is a mid-level ontology for energy systems modeling. It's developed in OWL-DL and contains roughly above 14,000 axioms. And well, our tool was quite performant. In less than a second, it produced more than 32,000 dependencies. That's already quite a lot, but quite performant again. So we tried to push the envelope a bit and looked at a larger ontology. In this case, SNOMED CT, which contains more than 1,700,000 axioms. And for that, our tool took 92 seconds to produce 6 million dependencies. Well, if our original use case was to use these dependencies to check for inconsistencies, we would now need to check all these 6 million dependencies for possibly unwanted ones. That's quite a task. So we need something else. And what we need on the next slide is a notion to filter dependencies. And as one does nowadays, our first approach was to use AI. And next slide. This approach works thusly. So we have our dependencies on IRs on the left-hand side, and we enrich them with labels and definitions from our ontology. And we package this into a prompt that we then feed to our LLM. And the prompt asks the LLM to check whether for a given class, the following dependencies are correct. We also supply a notion of what correctness of dependence means to the LLM. And then we give the class that we want to, the class on the left-hand side of our dependence with its label and a definition, and then all other classes that this class allegedly depends on, also with label and definitions. And we feed this whole package into the large language model, and hopefully it yields a result that says, okay, some of these dependencies are intended, some of these are unintended. So for example, here on the right-hand side, the participant of dependence for electrical energy was intended according to the LLM, while electricity export was not. Okay, so next slide. We now have, we used this approach and applied it to our two ontologies. And for example, for the OAO, we were able to find a bug, and you have already seen that. This bug that you have already seen earlier was also identified by our approach. Next slide. So we also tried to do this with SNOMED, and we were also able to find a bug here. So there was an axiom in there that said that the structure of the male urethral crest, apparently emptiness depends on the structure of the lymphatic vessel of female pelvis, which should be obviously not the case. So was apparently also a bug in SNOMED that we were able to identify using our tool. So everything's nice and dandy, right? We have a tool, we can filter our dependencies. The AI tells us everything that we want to know. We are good to go. Next slide tells us, unfortunately not. We used our LLM with two 12 gigabyte GPUs. So we were already leaving the realm of consumerware hardware. And we limited our request to 10 dependencies at a time. So each request took around 1 or 2 seconds. But 1-2 seconds for one request might sound little. Unfortunately, we have many dependencies. So for the Open Energy ontology, this whole ordeal took 90 minutes. For the SNOMED ontology, almost 10 days. For practical development approach, this is still of limited usability. You can, of course, apply this at the end of your development cycle. So you are at a point where you want to produce a new release, and you want to make sure that this release is mostly free of errors. So you're willing to invest a bunch of computational time, not manpower, obviously, to run this approach, and then use it to find possible errors. So there is some applicability for this, but it's still not satisfactory. So next slide. We want to do a bit more. So what if we, instead of considering the dependencies in the whole ontology, we look at dependencies across the development cycle? What if we look at, for example, 2 different versions of the same ontology and see how the dependencies developed over time? So here's an example. Consider we have 2 versions of the same ontology, version 1, version 2. We derive the dependencies using our Strix tool for both ontologies, and then compare them, meaning that we check which dependencies have been removed and which have been added. And this gives us a notion of what happened during this development. And next slide. In order to make this more accessible, we developed a tool for that also, which is basically an ontology viewer that also incorporates dependencies. So you can look at you can open your ontology, you can browse your ontology, look at given certain classes and see which classes they depend on, and so on. But you can also look at at different versions of your ontology. If you supply 2 different versions, it will create this diff of dependencies for you. Again, also open source developed. Next slide. Next slide should be a very blue screenshot for some reason. So this is the tool. This is our tool. On the left-hand side, as I said, you can browse your ontology. So here we selected the class good from the Open Energy ontology version 10. You can see then on the middle panel all the class with all its annotations. On the bottom, you also have axioms. And most importantly, on the right-hand side, you have all the dependencies. that have been changed from the previous version. Yeah, so if in this case, the previous version would be 2.9. And you can see that, in fact, a bunch of dependencies have been deleted from the previous, compared to the previous version. Yeah, so there was a dependency between good and monetary value, or physical unit, or currency. Those are all gone. No new dependencies have been added. Yeah, so this is a tool that you could use in order to check your dependencies across versions. But maybe you don't want to run a tool every time someone proposes a change to your ontology. Next slide. So we did one more thing. So most ontologies, or a lot of ontologies, are developed publicly using GitHub repositories. And this has one of the benefits that external contributors can also propose changes to the ontology. They can open what's called a pull request, which is basically saying, here I have this change that I want to see in your ontology. And we developed a small workflow that is basically a script that runs on GitHub itself that uses these pull requests in order to incorporate our dependency diffs into this whole process. So whenever someone comes up and says, here's a change that I propose, this workflow that we developed takes the current version of the ontology, the proposed version of the ontology, and creates the dependency diff. So the difference between dependencies between both. And puts this dependency diff as a comment underneath the pull request, so reviewers can see it and use it as an additional input during evaluation of the ontology, of the pull request. And next slide. We also created a small toy repository as an example how to use this workflow, where we use the pizza ontology, which, well, as many of you might know, contains deliberate errors. One of them is this axiom down here, which says that ice cream has a fruit topping. And well, in this repository, I have just a single pull request that proposes to remove exactly this axiom. And the automated tool then commented under this pull request that there have been some changes in the dependencies. And as you can see on the bottom left, these dependencies, the dependencies that were removed, were the ones between ice cream, fruit topping, ice cream and pizza, and ice cream and pizza base. So the ones that we actually want to remove, because the tool currently uses emptiness dependence. It means in the previous version of the ontology, it was the case that if there is no pizza, there can be no ice cream, which is not intended. So this tool can actually guide your ontology developers during the ontology development process to find possible bugs in pull requests. Also, these we have seen in our experiments that this approach doesn't just show unintended dependencies in the stuff that has been added to the ontology, but due to the way dependency traverses through the ontology, it also can show bugs in already existing axioms. So that was a nice artifact that we have seen in our experiments. Okay, so now this basically concludes our practical, so our current state of research that we have right now. Next slide. So what are we doing right now? So first of all, we presented 3 different notions of dependency here. There are many more. There are many more ways to actually look at dependency, and we have several other definitions that we could not cover in this talk. So there's more research to be done here. We are currently also looking into a proper user study, where we collaborate with ontology developers and evaluate how useful this dependency approach is actually in active ontology development. Can ontology developers use it? Is it helpful, for example, this pull request approach, to make ontology development more stable, less manual? Another interesting thing is that we are doing right now. we are looking at a generalization of this notion of dependency. In this talk, we consider just ontologies written in EL, DL, and so on. But of course, there are many more. Now, in our original publication on this topic, we considered logics that look like first-order logic, but there are, of course, many more logics. So one of our students used a logic-agnostic framework and defined dependencies in those. So now currently we are developing a framework that allows you to define dependency without a concrete logic in the background. So the system then means as long as you can plug your logic into the system, you can get a notion of dependency out of it, which is quite interesting and has really interesting effects depending on which logics you consider, for those who are more interested in the theoretical side. Okay, the next slide. Yeah, this is the slide that you have already seen after Fabian's talk. So we have seen the formal side of semantic dependency. And next part of the slide. Yeah, we now have seen that we can extend these, that we can actually apply these definitions, these theoretical considerations to actual problems in ontology development. Yeah, we can take this pure semantic definition of dependency that is too complex, define a syntactic calculus, and then use AI to filter important dependencies, or consider just dependency across versions or a combination of both to make dependencies more useful in actual ontology development. And so this hopefully can be a good tool that helps ontology developers along the way and is helpful to everyone. Next part. Obviously, this was not just done by ourselves, but we also have 4 contributors, namely Lily Gerlach, Colin Heidfeld, Benedikt Marschner, and Till Mosakowski. Thanks also to them, and thanks to you for listening.